So, welcome everyone. It's amazing to see so many people here today. Let me introduce myself. My name is Péter Gyarmati and I'm working at Shaper3D for 3 years now. Currently, I'm responsible for developer experience and security as an engineering manager. However, I spend most of my time as an individual contributor. I'm very excited to have this opportunity to share some of the work we've been doing behind the scenes at Shaper3D. As the title suggests, this talk is about Infra on steroids. Many of you probably figured it out, not we are on steroids, but the infrastructure itself. And this is about the CI/CD system that supports Shaper3D's engineering team. During this presentation, I take you through the journey of how we build this system step by step. So, is this still working? All right. I also share some of the lessons we've learned, the tools and processes we've implemented, and also what's next as we push the boundaries even further. Before going forward, let's talk a little bit about Shaper3D. At Shaper3D, we are revolutionizing the way people design and create. Our 3D CAD app is trusted by millions of users and iconic companies worldwide. These users bring innovative physical products to life. From cutting-edge gadgets to everyday items, there is a good chance something you own was designed with Shaper3D. We are not just building software, we are creating a platform that empowers creativity and transforms industries. To set the stage, let's talk a little bit about the problem space we are dealing with at Shaper3D. So we are building for 4 platforms: iPadOS, macOS, visionOS, and Windows. Each platform comes with its own quirks, edge cases, and unique requirements. All of these add a significant layer of complexity to both the development and testing of it. Our team consists of more than 60 engineers, and it's still growing. Everyone is contributing to the code base on a daily basis. With this many people collaborating on such a complex product, the potential for merge conflicts, regressions, or broken builds grows exponentially. The code base is huge, with around 3 million lines of code when you include third-party dependencies. On top of that, we also have a lot of pre-built dependencies that are included in the final packages. The shared cross-platform core, kernel as we call it, is written in C++. On top of that, we use Swift for UI on Apple platforms and C# for Windows. Building such a big code base and such a diverse code base as well requires significant amount of compute time. Testing a similar application is not trivial. To ensure the product's quality across platforms, we need to validate everything, from the correctness of the core logic, the user interfaces, and platform-specific behaviors. And this approach requires multi-layered testing approach, ranging from simple unit and integration tests to long-running end-to-end UI tests. As some of you may remember, during the last meetup, we had an insightful discussion on the topic of build versus buy. So let me reflect on that a little bit. We chose to build our infrastructure because off-the-shelf solutions simply aren't enough to meet our needs. Managed CI systems often lack support for all our platforms and fail to provide the level of customization required to optimize our workflows. By building in-house, we achieved both the flexibility, performance, and scalability necessary to meet our unique requirements. Let's take a look at where we are today. Currently, there are 3 dedicated engineers in the team, and me as an engineering manager, and everyone is focusing on maintaining and enhancing our development infrastructure. This system is only part of it. We are doing many other things as well. Our system currently handles more than 600,000 minutes of CI time each month. This volume reflects the scale at which we are operating, and this continues to rapidly grow. Each pull request can run up to almost 100,000 tests, and we build the infrastructure to scale even a lot further. We are running unit, UI, rendering, and performance tests, and also other types of tests on CI, and it also powers the release pipeline and various utility workflows. We are releasing Shaper3D more than 40 times a year, making it the most frequently released CAD application in the industry. Our infrastructure now includes 50 Mac Minis. Those are Apple Silicon M4 Mac Minis, and also 2 Intel-based ones to support our users stuck on legacy hardware. All of these are managed automatically. On the Windows side, we operate a large fleet of VMs, but those are currently under construction. I'll talk about it a little bit later. Lastly, we have achieved full CI system unification. We run all platforms on GitHub Actions nowadays. So let's rewind a little bit and take a look at where we started. So back then, there was no dedicated DevX team. I joined what was called the release team more than 3 years ago, and the very same day I joined, it was renamed to Build and CI. and I was the only engineer on it. After that, in 1.5 months, it was renamed to DevX, and a week later, DevX, and it's still called DevX, fortunately, and I got other engineers by my side, and we started to work on this challenge. So at that point, the iOS and macOS version of the application was already released, and the Windows version was still in beta, but we didn't even hear about what visionOS is. The infrastructure was very bare bones. We had 3 Mac Minis and 3 Windows virtual machines. All of those were set up somehow, and we didn't really know how. CI for iOS and macOS was running on GitHub Actions, while we were using Azure pipelines for Windows. However, there were no monitoring tools, no telemetry, and essentially no observability beyond the pass of fair result of CI checks. You can imagine this made it quite hard to debug anything, basically. To make things even worse, and for me it was the most painful, developers had zero trust in the CI system. Many believed it was completely unreliable, and the sad truth is they were right. So most of the failures were assumed to be false positives, and we had to debug all of these. This was the starting point, and you can see we needed to improve this quite a lot. So let's see how we approach this problem. First, we started focusing on the stability part. To build a reliable system, we have to start with the foundations, the infrastructure itself. As I mentioned, at the time we had 3 Mac Minis and 3 Windows virtual machines. These were set up manually by 3 different engineers on each platform. So no surprise, it resulted in a heterogeneous environment with a lot of inconsistencies. So all of them had different minor OS versions, different compiler versions, and many other things, just to highlight a few. And you can't rely on such a system. So our first step was to fix these inconsistencies. Initially, we standardized everything manually just to unblock developers. But when the time came to set up new machines, because it came out very quickly, the 3+3 machines were basically nothing. We had to set up new ones. We realized that manual configuration is quite hard, especially if we have no clue what we need to set up. So before investing further into the current setup or automation, we took a step back and evaluated our infrastructure options. For macOS, proper virtualization was not a viable choice. The available solutions at the time were either very expensive and still required dedicated hardware, or introduce an additional abstraction layer that would degrade performance, which was one of the most important things for us. On Windows, running UI tests meant we couldn't rely on headless solutions, such as containers. Thus, we opted for virtual machines. Circling back to the pain of manual configuration, what do you do when you don't want to do that manually? Well, we are software engineers. It's in our DNA. We have to automate it. So in this particular case, using infrastructure as code tools. We chose Ansible for this purpose, and the reason is there are a lot, but it's compatible with both macOS and Windows, and also other operating systems if we want to extend our portfolio. And we were able to standardize the configuration across our infrastructure and significantly reduce the time to provision new machines. How many of you were here at the first DevBP Meetup? All right, quite a few. So you might remember how Ákos talked about engineering design at Shaper 3D. So this point in time was when we wrote our first engineering design document, and here it is. As you can read, setup and configuration management of macOS CI agents. So initially we only rolled this out for macOS, and then later on extended it to Windows, basically the next week. And you can see the design goals as well. It's the same as I highlighted right now, but a bit more technical and a bit more detailed. So after automating the infrastructure, we encountered another set of challenges. So dedicated machines have a lot of benefits, like performance, but they come with their own downsides as well. So machine can face issues like unexpected reboots, running out of disk space, network failures, or many other stuff. And without observability, as I mentioned, these problems often cause CI failures. And there were countless times when developers came to us that, oh, my UI test failed because there is no more disk on the Mac Mini. So yeah, it was kind of embarrassing. So this only worsens the lack of trust developers had in the CI system. So we needed a solution that could give us insights into the health and the status of our system. So with proper alerting, we thought that we could address some of these issues proactively, like running out of disk space, while also resolving them quickly when encountered retroactively, like unexpected reboots. So, to tackle this, we rolled out a monitoring solution. Initially, it was built using Prometheus and Grafana, along with Node and Windows Exporter for metrics collection. But since then, Grafana rolled out a lot of stuff. So we've upgraded to fully leverage the Grafana Cloud Stack, which uses Grafana agent for both for metrics collection on both platforms and also for metrics forwarding. So it's quite easy to use it right now, and it's beautiful, as you can see there. So this is how a macOS monitoring dashboard looks like. There you can see the CPU usage, load, memory usage, disk usage, etc. And there are actually many other things, but I couldn't make a bigger screenshot. So to go back to it again, this was our second design document. We created a lot more. I think I made my point. I'll stop showing them now. So one of the next steps in improving stability was simplifying our CI tooling. As I mentioned, we use GitHub Actions for iOS and macOS, and we use Azure Pipelines for Windows, but this was a lot of overhead. So to reduce it, we decided to consolidate it into a single system. And because Azure Pipelines didn't support all of our platforms, it was quite easy to decide. It was GitHub Actions now. So since then, we are using GitHub Actions with all of its beautiful failures. And to my favorite or least favorite part, dealing with flaky tests was one of the biggest challenges we faced, and it's still a problem. So for those unfamiliar with the term, flaky tests are those that can both fail or succeed without any change to the code or the system running it. So as you can imagine, based on that, they are a pain in the ass. And we had to do something about it. So to determine if a test was truly flaky or failing as expected, we needed consistent data analysis. However, we used a lot of frameworks across platforms for a lot of different tests, so all of them produce different result format. So first, we built a system to parse and centralize test results in a unified format and leverage Databricks for long-term storage. It was quite easy because we had a data engineering team and we had to just use their stuff. And this allowed us to create dashboards and define heuristics to effectively identify flaky tests. So based on this, it turned out that fighting with developers were for a reason, because a lot of tests were indeed flaky. So to avoid causing friction for developers and to not disable most of the tests right away, we implemented retry mechanisms to ensure flaky tests wouldn't block pull requests. So this was already a huge improvement for the developer experience. And at the same time, to not just let it rot and just retry many times, we started collecting data to these retries to evaluate the flakiness of each test. If a test exceeded the defined flakiness threshold, it was disabled and manually delegated back to developers for fixing. So it was also quite painful. So over time, we further automated this process. Today, flaky tests are detected and disabled automatically with Jira issues and PRs created by the system to minimize manual overhead. So we are disabling the flaky tests basically on a daily basis now. So here you can see the dashboard that we first published to developers. And it looked a bit different back then, but I couldn't make a screenshot because Database just updated the UI. And fortunately, there is dark mode now, so it's a lot prettier. And you were able to use this to check whether your test is flaky or not. As you can see, there are the green ones, the successful runs, and the red ones are the failures. And now there are gray ones disabled. This is actually a real flaky test from last week. And you can see it was disabled on the 13th of January. It should have been a bit before, but that was a weekend. So we did it on Monday. So after we achieved a reasonable stability, we started to focus on speed. So the first thing was an umbrella project, caching, and it became a cornerstone of our efforts to accelerate workflows by eliminating a lot of redundant work. So it's quite a powerful tool for improving speed, so we addressed a lot of challenges under this. So the first one was quite trivial, and most of you wouldn't check it as a caching, but incremental checkouts. So rather than downloading the whole repository for each CI run, we only fetched the changes since the last run, and it saved more than 20 minutes for each run. So it was quite an easy change. And also the dedicated machines let us do this. The next one was incremental builds. C++ builds are notoriously slow and very, very painful, and clean builds for every change were simply not feasible. So by building incrementally, we drastically reduced build times. The third one was compiler caching. Tools like Ccache for C++ provide both local and distributed compiler caching, so it's allowed us to reuse previously compiled code. Next, we looked at optimizing how we run CI checks. So previously, we ran all the checks on all platforms for every changes. So yeah, that's a lot of wasted resources. To avoid that, we decided to implement selective pull request checks. For example, if a pull request only changes Windows-related code, like on the picture, we now skip running checks for Apple platforms. As you can see, the Apple one was skipped right there. And it's the same the other way around as well. Similarly, there are like edge cases. For documentation-only updates, we skip everything. You don't need to run checks. So this not only saved time and resources, but also provided faster feedback to developers, and it allowed them to iterate a lot more quickly. So another key step was organizing our tests into different test suite tiers. And this was a great way to balance speed with thoroughness. For pull request checks, we only ran a lightweight set of tests, focused on ensuring the code doesn't introduce obvious breakages. Next, after merging, for master runs, we execute a more comprehensive test suite to catch deeper issues. Lastly, nightly tests run the full suite, covering long-running tests that aren't practical for every PR or commit. There are tests that run for literal minutes, so that's not something that you want to run on your PR checks. I like this approach because it ensures faster feedback during active development while still maintaining high overall quality assurance. And this way you can tweak it quite well to tailor it to your needs. Last but not least, we addressed one of the biggest time sinks in the CI process, running all tests sequentially. To speed things up, we parallelized our test runs across multiple machines. The key thing to making this efficient was sharing build artifacts between test runners. Instead of rebuilding the code, which takes actually a lot of time on each machine, we reused pre-built artifacts, and this way each machine could focus only on executing its set of tests. After these projects, we took a step back, and we wanted to reassess our journey. So balancing speed and stability is critical, because a fast system that's unreliable disrupts workflows, while a stable but slow system bottlenecks productivity. To focus on this, we made several targeted improvements. We introduced manual code signing on Apple platforms to reduce random failures caused by Apple servers, which was actually a lot more common than we thought. We switched to a new Mac provider for greater stability. This reduced outages by a magnitude, and actually it was less than half of the price, so it was a great deal. We optimized Windows VM configurations for better performance, and we fine-tuned our build settings many times to improve compile times. And these are just a few, which I thought was worth a mention. But the thing is, it's still slow. Does this mean we did a bad job? Maybe, but I don't think so. Building such a system is hard, very hard. It's like swimming against the current while your hands are tied back. Maybe I'm exaggerating a little bit, but the code base is growing, new tests are added, new platforms are introduced, new dependencies are introduced, and many other things, which makes our life quite a bit harder. So it's hard, but I think this challenge is fun. And some people ask me in our engineering team, why? And I think it's because it's challenging, and I think it's quite rewarding. And most importantly, such a job makes a huge impact. So far, it might seem that we did everything perfectly and it's just slow by accident. So, well, not exactly. Let's take a moment and check what we messed up, because there were quite a few things. So, first, the introduction of incrementally build seemed like a promising solution for distributed builds during some POCs. Well, I see some faces about incrementally build. Yeah, I know. So after purchasing it, when we started to productionize it, it turned out it was too good to be true. And we wasted a lot of money and engineering resources on it. And in the end, we just throw it out. So it was quite painful. Next, we underestimated the complexity of code signing when updating certificates, and we caused quite a few outages. Another issue was underutilization of our features. So we built quite powerful features and solutions, but we didn't really communicate it with developers, so they didn't even use it. So there they were, great features without anyone using it. So yeah, we learned a lot from that. Finally, We sometimes prioritize projects without feedback because, of course, we know better than developers who actually use the system on a daily basis. And yes, this led to working on solutions that actually didn't solve any pain points. Only ours, but that wasn't the reason we started working on it. So each of these taught us valuable lessons, and we learned quite a lot since. So as we look ahead, here are some things that are coming soon. So I teased it a little bit when I talked about the infrastructure, but we are actively working on auto-scaling our Windows infrastructure. And auto-scaling nowadays is relatively straightforward. There are a lot of managed services, but making it efficient and tailored to our needs is a complex challenge. And we are focusing on it right now to get the most out of the system. This is also a project where we're utilizing caching quite extensively. So another significant undertaking is revamping our build system. So this has been postponed several times because of its complexity and cost, and sometimes because I didn't want to do it. And instead we optimized some smaller stuff, and we didn't really do anything big about it. But it's time to take on this large project and create a system that meets our long-term needs as well, not just, we shouldn't just focus on low-hanging fruits. So we also keep tweaking our test suites. It's a continuous effort. We need to find the right balance between thoroughness and speed. Lastly, as I mentioned, we are quite a small team, and we are supporting other teams. So we have a lot of maintenance thing going on as well. So we'll keep automating repetitive tasks and maintenance things, and this way we can free up our bandwidth for high impact work. And beyond these, there are quite a few things on our roadmap, but I will be running out of time, so I won't talk about those. But the future is quite exciting, and I can't wait because there is plenty more to come. As we wrap up, let's focus on some key takeaways from our journey. First and foremost, stability is the foundation. Without it, you can't rely on your system, and nothing else you do will truly matter. Second, trust is just as important as stability. Developers need confidence in the results the system provides. But building this trust is not easy. It requires both a reliable system and clear communication about what's happening under the hood. Third, speed is a game changer. Improving the velocity of your workflows and processes can have the biggest impact on engineering productivity. It's not just about running tests faster or building the applications faster, it's about enabling engineers to move faster overall. And from business perspective, probably this is the most important part. Fourth, reduce mental overhead. Engineers should focus on solving business problems, not wrestling with CI configurations or infrastructure issues. By abstracting these complexities, you empower them to work more efficiently. Fifth, balance is everything. A fast system that is unstable or a stable system that's slow won't serve your team well. Optimizing for both ensures you get the best of both worlds. Finally, iteration is key. Achieving big improvements often comes from small, deliberate steps. Each iteration builds confidence and sets the stage for the next improvement. So these lessons have guided our progress, and I hope they offer valuable insights for you as well. And I couldn't leave this out. So if you found the challenges and solutions we discussed today exciting, I have a great news. We are hiring for the team. So as I mentioned, it's a small, high-impact team, and there is plenty of opportunity to make a real impact. If this sounds like a fit, please either hit me up or there is the QR code and just press apply.